So it's my great pleasure to introduce Jérôme Faist, or as we call him in my house, the other J Faist. And well, Jérôme is originally from Switzerland, his PhD in EPFL in Lausanne. Then he moved to IBM Rüschlikon for first postdoc for 2 years. And then moved to Bell Labs with Federico Capasso, where he was instrumental in developing the quantum cascade laser, which he has won and countless prizes. I'm not going to list. But then he moved to Switzerland, actually to Neuchâtel as a professor for 10 years. And after that, he moved back to
Zurich. The German-speaking part.
ETH Zurich in 2007, where he's a professor at the Institute for Quantum Electronics in the Department of Physics. And in terms of research, he has a very broad program. Has been working with quantum cascade lasers and so on. He has worked on quantum Hall frequency comb lasers recently that are very interesting. And specifically in the last few years, he has been very interested in the effects of, let's say, vacuum fluctuations and on the one hand, measuring them directly. And what we will tell us about today is actually using them to modify physical effects such as the quantum Hall effect. So we're really looking forward to it, and thank you for coming to this.
Thank you, Johannes. Thank you for the invitation, and thank you for being here. It's really nice and great to see also friends from all times and young people. So yes, indeed, I'll be today talking about manipulating quantum Hall effects with cavities. And but first, I would like to really acknowledge, the work of two amazing PhD students, Lorenzo Casiotto, who is now working on this, Josephine, who just graduated, Engner, who just graduated a few months ago, and also really, and that's, of course, can never be said strong enough, the group of Werner Weckscheider, who grew those fantastic two-dimensional electron gas with super high mobility that we are using. And this is, of course, a great thing to be able to take advantage of such fantastic material. So, last time it worked. This is really interesting. See, I checked it and it was working. So, maybe I should do okay. Maybe it works. Okay, yeah, this is great. It seems to work. Okay, I know it works now. Okay, so anyway, I think I will just click with my hand. That's nice as an experimentalist. So let's say the idea is really, if you study solid-state matter, basically what you do is you try how to understand it, is you try to modify a parameter and you see what is going on. And so those parameters can be pressure, they can be, I'm afraid this is really not cooperating. Huh? It's crazy because we checked everything half an hour ago, and it was working like a charm, and it's now yeah, okay, maybe I should make sure that okay, good, all right, so now it works. Okay, so it's maybe I think I should not use the pointer, and okay, whatever. Temperature is a parameter. Put a magnetic field. This is, of course, something we love to do as a solid-state scientist. You put yourself in a magnetic field. You actually, of course, now recently, another fancy technique is you take two materials, you put them with a slight angle, you create a superstructure. It's so-called moire engineering. And then, obviously, if you like lasers like I do, you can also do optical pumping. So you shine light on your sample and you see what's going on. What I would like to discuss today is how can we manipulate matter using cavities, and not cavities in the meaning of just saying, oh, let me make a laser and let's put the laser inside the cavity and then let's see how things move. No, what we want to do is really cavity QED control, and so we want to use the vacuum fluctuation. Now, vacuum fluctuation, we know that they have an effect on atomic physics. So we know that, for example, the Lamb shift arises, and it is a splitting between the two S1 half and the two P3 half state of the hydrogen atom because this hydrogen atom is subjected to vacuum fluctuation. And those vacuum fluctuation, you can see them, and there is a very nice model by Weldon in 48, which just said, well, let's imagine this thing is like a random noise. I have an electric field noise, and that noise will affect differently the different orbitals. And depending on the shape of the orbitals, some are going to be stark shifted on average and otherwise less. And therefore, I see this small shift, it's 1 gigahertz, small shift of the energy state. There is another very classic paper of the 48, same period, is the Casimir effect. You take two metallic plates, you bring them close together, and basically the vacuum fluctuation are responsible for, if you want, radiative pressure. You should not say, oh, those are photons that are bouncing against the metal. No, because there's no photon. So it's really fluctuations. And basically, one way to see that is to say, well, the density of state between the metal is not the same density of state for allowed modes outside of the metal, outside of the two plates, and therefore there is an unbalance, and that unbalance creates a pressure. And what is, of course, interesting is that somehow those vacuum fluctuations, they also exist in cavities, and you can use cavities to, for example, enhance, and that was the proposal of Purcell, still in 48 or so. And he really, actually, if you look at the paper, that paper is like, 1 column long. So it's like, extremely short. It's amazingly short. It's kind of not even a page. It's just like one little column. It's like an abstract of a conference. And basically what he says is, if you take, a nuclear resonance in the microwave, and you ask yourself, okay, how much time does it take, to have a spontaneous emission from the, one state to the other state of that nuclear resonance? He finds amazingly long times, which are, 10 to the 21 second, which is a bit too long to wait. And therefore said, well, how can we sort of force this thing to emit faster? Well, let's put it in the cavity. And because of the cavity enhances, if you now provide, because the problem is, why is it take so long? You can think of it simply because there are, at that frequency, very few states accessible. You have plane waves, but they have so long wavelength that they basically, your tiny atom is trying to couple to this amazingly long plane waves with such long wavelength, they don't couple, basically. And so what you do is you put in a cavity and you create a mode at the right frequency, and then you can enhance by, in that paper, he predicted you can enhance your effect by something like 13 order of magnitude, which is kind of a nice effect. So anyway, just the point is, the background, if you want, of what I'm going to be talking about today, is really this idea that we can take a cavity and we try to do things that look like a Purcell or, a Casimir, a cavity, and try to do something like a Casimir or like that lampshade. So in other words, what we try to do is we take solid state matter, we take a cavity, vacuum fluctuation inside, we put the solid state matter inside the cavity, and we magically create an effective interaction. Now, of course, this sounds like a bit magic, and it is a bit, if you stay at that level, because, of course, you don't expect much effect to happen if I were just to do the experiment this way. And let's say, these experiments, now, let's say before, let's say there is actually in theory now a lot of paper that really predict that you should be maybe able to control with cavities such phenomena as ferroelectricity, superconductivity, and ferromagnetism. So what we actually want to do is, in my group, what we're trying to do is to control electron transport using cavities. So, naively would say, well, I have electrons, they are standing in this potential, this is the, lattice potential of my solid state, and then I'm using a cavity and I'm trying to move those electrons inside the cavity by this vacuum fluctuation. And, if you look at it this way, it doesn't look like a very easy thing to do, because you think, well, I have, again, much more modes in if I compare the number of phonons that I have with the number of photons, of course, the phonon, there's an enormous more number of phonons than photons. So it looks like it's a difficult thing to do. So one key essential aspect of it is to think of which cavities do you want to use and what are you going to be trying to affect. So the cavities you tend to study in quantum optics are some things that look like two mirrors, they have a high quality factor, and you put atoms inside. But then as a result, what you have is typically the atom has the Bohr radius type of diameter. The wavelength is the one of the visible. So you really have the so-called dipole approximation because your wave function is much shorter than the wavelength. And you basically have also relatively limited vacuum fluctuation. Now, what we want to do is to do a different type of cavity. It's so-called circuit-based cavities. Now, you should not think of mirrors and a cavity in that sense, but what you should think is this is effectively an LC resonator. And so why do you want to do this? Well, because you see, the vacuum fluctuation, you can understand them really in this very simple harmonic potential model of one mode. You know that if you quantize the electromagnetic field, you basically map the Hamiltonian of, you usually take a cavity, usually you map the modes of those cavities to harmonic oscillators, and then you say, well, I know how to quantize the harmonic oscillators, I know the energy of the harmonic oscillator, and the ladder of energies of the harmonic oscillator is 1/2 h bar omega plus h omega each time I add a photon. And now the idea is, well, if I even leave my cavity in the ground state, this 1/2 h bar omega is an energy that stays and I cannot remove. And that energy has to be, half of the time at least, under the form of an electric field. And that electric field, therefore, is inside the cavity. And therefore, since the energy, this fixed energy, 1/2 h bar omega, is spread inside the volume of your cavity, if you can make the cavity very small, of course, if you make that volume very small, then, of course, the electric field has to be larger to just compensate the fact that you have less volume. And that's why, you can write that the vacuum field is proportional to 1 over the square root of the effective volume of that cavity. And now, what is good with those LC cavities is now, where is the electric field? Is in the gap of the capacitor, and the capacitor, in principle, you can make it way, way shorter than the wavelength, and therefore you can reduce the effective volume of the cavity by many, many order of magnitude. Now, then, of course, there are features that are quite different in that cavity. But the last thing I want to mention also is, usually what we will try to do is not to couple to a single atom, because what we are interested is in excitation of a solid state matter at low temperatures. And those typically are collective excitations of the electrons. And those basically have the effective wave function, if you want, that you're looking at is effectively given by the current's length of whatever excitation you're considering. And that, of course, can be much larger and longer than the size of the atom. So you can have excitation at 10 or 100 nanometers long. And that's why, in the end, we are in a regime where on that length scale, the field, because you are looking at the field inside this capacitor, may have a very strong gradient. So in the end, you have a system where you can have significant field gradients over the wave function you're talking to, which means you're effectively doing high field physics, but with vacuum fluctuation. And so this is a completely different way, it's a completely different game, if you want, because you have, usually high field physics, you do it by taking a very large laser, focusing it and blasting your sample with as much, field as you can. Here, you actually not really blasting it because you're using simply this extremely strong fluctuation locally that has this very large gradient. So just as a recap, I mean, if you move now from a free space cavity, in free space cavity, you have a plane waves. The electric field is perpendicular to the magnetic field, perpendicular to the propagation. In LC resonators, you basically have the electric field and the magnetic field may be actually at different locations. They're not at the same place. It's completely fully authorized because you're within the wavelength. So, you absolutely can have this. But you don't have fixed charge. If you're reading electrostatics, then you have fixed charge, and then the magnetic field is zero. And that's basically what we are being studying, is something which you might say is a bit in between. It has some features of electrostatics, but really what is important is it's still an AC excitation. Okay, so what I would like to claim is, if you're trying to look at effect of vacuum fluctuations in solid state, the quantum Hall system is a great way. It's a great tool to do that. Why? Because in that quantum Hall, we have a very strong light matter coupling. And that just comes because of the electron in gallium arsenide has a very low mass. And that means also that because it has a low mass, it couples very well with electromagnetic waves. And you can see it, for example, by those polaritons that you can create, which are collective excitation for light matter excitations. And I will discuss another important aspect of that system is that in most of the regime, the transport is quantized. And remember, what we wanted to see the effect of vacuum fluctuation on transport. And therefore, if you start from a system which is quantized, then it's much more easy to identify that whatever is doing the work is vacuum fluctuation, because you know where you start from. You know that it should be quantized. And then you're looking at the deviation from something that you know. And the other thing, which is very important, is that we have a system, and that's realized, of course, as we'll see, if you put a magnetic field perpendicular to the electron gas, you have so-called Landau levels, and those Landau levels, they are flat. So what it means is, in terms of now solid-state physics, it means that I have electrons that have all the same energy, all the ones that I have in this Landau level, they have the same energy, and because of that, don't have any effective kinetic energy, and it means that interactions, of course, play a very important role. So you can both study the cavity effect on single particle and composite experiments. So just what do we talk about? What do we need to know about this system that we're studying? Well, think about, you have electrons, they are distributed on the plane, you apply magnetic field, they do cyclotron orbit, and now if you look at this in the quantum matter, in quantum way, you can show that this corresponds to creating a harmonic oscillator with equidistant levels, and the levels are separated by the cyclotron energy, and the cyclotron energy is of proportion to the magnetic field. So the beautiful thing also is that we have a system where by changing magnetic field, we can basically change the energy scale of the system. And now, the other thing which is very important for us is that this system is such that you can make easy optical transition between those field Landau levels and the empty Landau levels, and those transitions are optically allowed, and they are very strong. So you can absorb a lot of light, and this is basically what we will be coupling. So now the other aspect which is very interesting is the transport. So the type of sample we will be studying are so-called Hall bars, and try again to see whether I can point the it's going to be strong effect. So, you can pass a current in this way, and what you do is you measure both the so-called longitudinal resistance and the transverse resistance. And now, what you see in the quantum Hall is that depending on the Fermi level, that means you have, depending on how high your Fermi level is, if it is within the Landau level, what you see is a finite resistance, longitudinal resistance, and a non-quantized transverse resistance. Whereas if I can place my Fermi level between two Landau levels, then I see now that the resistance is quantized, the transverse resistance is quantized, and the longitudinal resistance goes to zero. And that is, of course, very important. Why? Okay, there's an additional complication, if you want, is that in gallium arsenide, the electron can have spin up or spin down, and now the magnetic field lifts this degeneracy, and effectively, we have two sets of Landau levels, the one for the spin down, the one for the spin up, and they are separated by a gap, which is given by the effective Zeeman splitting energy. And that's going to come out afterwards. But then what is important to remember is the so-called edge state picture of this effect, meaning that you can think of the electrons are moving on the edge in 1D channels that are not backscattered. So in the modern picture of the quantum Hall effect, what you say is that you created a topological insulator, and meaning by that, if you think of the electrons in the center of your sample, those electrons, they cannot move because they're doing simply cycles on orbit. So they are not contributing to transport. The only electrons that can actually contribute to transport are the ones that are bouncing on the edge. So they like going, they are moving along the edge, and they can move only in one direction. And that's because even if you have an impurity, as Büttiger showed many years ago, you will hit the impurity, do a gold circle, and then continue happily going. So an impurity, a single impurity, cannot backscatter the electron. So once you have an electron on the edge, it will sort of move always in the same direction and never come back in that picture. So this was a system that we're looking to perturb with our cavities. The cavities themselves, as I said, they are these LC resonators, which we do by patterning a high conductivity metal layer in this funny shape. But what is important, of course, is that we pattern it directly. In the first experiment, we were patterning that directly on the sample, and we made the whole bar exactly fitting in this. So we can hope to have the maximum effect by having exactly this whole bar that where we measure transport fitting exactly in the resonance. And because we have this small volume, we can enhance the vacuum field to values about 5 meters per volt, volts per minute. Because we have a volume which is effectively 10 to the minus 4 lambda. So now this is a simulation to give you a finite element simulation of what you should see inside this cavity in terms of vacuum fluctuation. And two things I want to stress, this is a bit below the gas, is that you have this, edge here, and as you'll see, the field is actually strong on the edge than it is in the middle. But basically, you have this field which extends inside the middle. So the experiment, we do it at very low temperature. So we do it inside the dilution refrigerator, and we don't, we try to keep the temperature as low as we can, 30 millikelvin. So at 30 millikelvin, you can really think there is no photons around, and they are all absorbed. So it's really we're dealing with the ground state of electromagnetic field. So if you look at 100, exactly, the log of the population of our resonator is minus 150, so it's really small. So the first experiment we did was, well, we take a whole bar, we put a resonator on one side, no resonator on the other. When we measure the part that has no resonator, we see exactly what we expect to see, which means, you see nice quantized plateau here, and you see very nice zero logical resistance when the plateau is. And then when we put the resonator, we see that all hell breaks loose. And we have, where the arrows show, you see that we've lost the quantization completely. Now, to make a long story short, the initial explanation, which still remains completely true, is provided by Cristiano Ciuti, is that we have an effect which is a anti-resonant scattering. And so the idea is, you see, because your cavity cannot give you energy, it's vacuum. So what you can do is you can kind of borrow energy from the vacuum under the form of an excitation, if you want. So what you do is you say, well, I take an electron, it goes up, and at the same time emits a photon, and then goes down and absorbs the photon. And now, each one of this step, of course, does not conserve energy, but you do it quickly enough so that it remains allowed, because in the end of the process, you have not lost any energy, so it's allowed. So this is a so-called anti-resonant process. So of course, it works, it's important only if you have a very strong light matter coupling. So this allows you, if you want, to move the electrons, and this allows you to now, if you want, counteract this topological protection that you should have of the quantum Hall. And this is why, in a sense, we lost the quantization. Now, I would like to sort of go next to the next experiment, because I think it's kind of, this was the initial experiment, and this initial experiment was really about having a sample that you put on the 2D gas, and do the measurement this way. Last experiments, they work in a different way. Because, you know, of course, when you actually put a metal on top of a semiconductor, you always feel like, well, maybe I'm changing something else. And I don't know what I'm changing, but I'm changing maybe something. And that something maybe is the reason why we observe this effect. So we move to a different experiment where now the idea is we have two separate systems. We have the whole bar, which is down here, and this is the whole bar, and then we have the resonator. And now, of course, we can move the resonator, as is shown here. We can move the resonator in situ and bring it close to the whole bar and vice versa. And this way, we can actually change the coupling between the light and the matter, because we can continuously change how strongly the whole bar is coupled to the matter. And here, of course, I do not have time to explain, but we quantify this light matter coupling by the time, if you want, the rate at which you exchange energy between this electronic excitation and the photon. This is called a Rabi coupling. And we can basically move that Rabi coupling from basically nothing to 30%, which means that the energy, let's say the frequency at which you exchange energy between the excitation of the electrons and the photons is 30% of the frequency of your cavity, which is a lot. It means that you're constantly exchanging energy between your solid state system and the cavity. Now, this is what we observe. So this is now the full measurement. And, you know, the color code is that when we are far away, it's this light green, and we are very close, it's this dark blue. And what is striking is the effect is not as impressive as the one I showed before. And the reason is that we are, of course, we don't touch. We sort of stayed at like 0.3 micron away from the surface. But what is striking is we see effects basically everywhere. And that, well, so spend a bit of time on this. And the first thing that we saw, now we could see really systematically what was happening at low field. And what is happening at low field, first of all, is you see at zero magnetic field, nothing happens. The mobility, everything stays the same. However, you see also that you have this alternance of even and odd minimum. The even minimum corresponds to your Fermi level being between two cyclotron splitted levels, while the other corresponds to your chemical potential being between two Zeeman splitted levels. And so we realize that, you know, if you zoom here, for example, as I'm bringing the cavity closer, this Zeeman splitting seems to be less and less efficient. And one way to measure that is to simply say, well, I can move my cavity at some point and do a thermal activation of that minimum, move my cavity to the next point, redo the thermal activation, and so on. And in this way, you can basically extract the effective gap of that. You can extract the splitting between those two states because you've measured as function of temperature, and your temperature is kind of your energy measurement. Then you can measure that as function of magnetic field. And now what you can see is as I'm bringing the resonator close, this splitting, this effect, this gap decreases, and it means I'm bringing the Zeeman gap closer. Now, the Zeeman gap in a 2D, in such a 2D electron system is not just given by the Bohr the Bohr magnetron times the magnetic field. It is enhanced by electron exchange. And the reason is, what I'm doing is I'm asking myself, okay, how much energy do I need to add an extra electron on the upper state, on the upper, let's say on the upper Zeeman level? And that means that in particular, this energy cost, of course, involves the exchange energy because I'm flipping basically one electron spin. And then therefore the exchange interaction changes. So our interpretation, and actually the interpretation of Christian Schutte, was that this exchange energy, which is extremely important because it's actually the one that dominates the G factor. The G factor here, you see, is 6. The effectiveness G star is 6.5 when we have no cavity, and it goes down to 4 when we have the cavity in close proximity. And that change basically is continuous more or less as we change. Here we've plotted it as function of the radio frequency, so it goes down. So there's of course some fluctuations, but then the model is that if you actually now make a model of these electrons inside a magnetic field that has a field gradient, and that's of course a key aspect, you basically can enable now an electron-electron interaction via the cavity. So what you're effectively doing is you're adding a new term to electron-electron interaction, which is not a direct Coulomb interaction. It's a cavity-mediated attractive interaction. And that attractive interaction results, in a sense, in this reduction of the exchange energy. And I'm going to say let's say this effect is, in the end, the strongest effect that we see, because we see it in all samples. It always works. And let's say, in the initial experiments, we of course had it, but the problem was that we had not this tunability and this ability to control exactly the effect, and that's why we could not really identify it this way. Now, the next step is, of course, you can ask yourself, okay, can I also do something to the fractions? And first of all, what is, okay, like the 5 minutes tutorial on the fractions, the idea of the fractions is that you now don't consider the electrons as being, the fractional quantum Hall effect appears as a collective effect of many electrons together. And many electrons that have this Coulomb interaction, they have no kinetic energy, and therefore they try to look for the best state that will minimize the energy. And they find that if you have, it's sometimes better to basically take one electron and associate with it two flux quanta and create a new quasi-particle, which is the so-called composite fermion. And now, instead of having a transport of single electrons, you do a transport of composite fermions. Now, effectively, so the idea is that once you create those composite fermions, you interpret the quantum Hall, the fractional quantum Hall effect as an integer quantum Hall of composite fermion. So the idea is you first build a new quasi-particle, and then you say, oh, that quasi-particle does a quantum Hall. So here, in our case, of course, to see this effect, you need to have a system which is very clean. And there, of course, this is why having those fantastic samples is so important. And also low enough temperatures and large enough magnetic. In our case, we will be focusing on this region. And that region corresponds to between filling factor 1 and filling factor 2. You can see that here, when we go, before the magnet quenches, 11.8 Tesla, we are 11.4 or so, we see another fraction, and that's the only one that we see, that would be the only fraction we see above Newton's 1. So we sort of concentrated on those fractions which are between Newton's 1 and Newton's 2. And now what is really completely surprising, if you want, is as you increase the coupling here, we are actually improving the quantization. And if we do the same little trick that I showed before, that means you position your cavity at a certain distance and then you measure your transport as function of temperature, and you look at what the activation temperature of those minima are, you find that the activation temperature of the fractions, 5/3, 7/5, and 4/3, they all three improve as you enhance the light matter coupling. So it is, if you want, quite, we saw that the cavity sort of quote unquote destroyed the odd integer quantum Hall. Here actually seems to be doing the opposite. It sort of improves the fractional quantum Hall. Now, in a sense, a word of disclaimer, if you tell me, oh, how do you compare that? Is that temperature better than the best sample of that, let's say, the best measurement of that sample? No, it is not. So what I mean, if you take a very large sample, where it's known that very large samples, if you take a large physical sample, and it's not a tiny hole bar, you will get a bit of a better, you get, I think, something like 2,000. So it's definitely above. But what is clear is that in this case, we've been able to improve the quantization of certain fractions by bringing this resonance. So there again, there is actually the same mechanism, electron-electron mechanism was invoked by the group of Cristiano Ciuti and also Regnault to, again, this modifying the famous Haldane potential, for those who are aware of this thing, the Haldane potentials of the fraction are modified because it's not enough to have a uniform, it's not enough to enhance or decrease the Coulomb effect. You need to modify those Haldane potential, meaning you need to change the ratio of the long range versus short range interactions. And let's say the claim is that in that case, for this 1/3 family fraction, we see an enhancement of the fraction. So now the last thing I would like to discuss, leave a bit of time for questions, is another collective effect that you see in the quantum Hall effect. And this is so-called the stripe phase. The stripe phase was discovered experimentally, was predicted actually also in the same years. And it really happens, those are kind of historical measurements, as an effect that appears not when you're fully quantized, but when you're between quantized plateau. And what happens is if you have a half-filled Landau level, the question is what happens to that half-filled Landau level? And there, the evidence was that at those half-filled Landau level, you can start to have a situation where there's a strong anisotropy between the conductors, depending on whether you measure it in one direction or the other. And the interpretation of that work was that actually, yeah, we don't have a Portuguese edition of the initial paper, Bachelorski, 95 and 96. Basically, the idea is that spontaneously there's a competition. You have this half-filled Landau level, and there's a competition between exchange energy and mean field Hartree energy. And let's say the system prefers gathering, if you are putting the, allowed, if you want it prefers, if you want, to minimize the exchange, and even if it costs it a bit of Hartree term. And that will appear if you have, like shown here, a last partially filled level on top of a number of already filled levels. So it's you need to have a background of electrons, and then you're looking at the last electrons. And it creates stripe phases. Well, the fact that it stripes is not clear. I mean, the electrons try to gather together. It's a bit like, if you have a liquid that you put on a surface, and try to make droplets or lines, the shape of this thing depends. Now, the reason we got interested is, again, we were not looking for that, and we had this type of measurements for a long time. And what we were seeing is an amazing anisotropy, or amazing change, when we are comparing the transport between quantum Hall plateau of a sample that had a cavity that looked like that, like just a rectangle, if you want, and a sample that had no cavity. And here in dotted line is the resistance that we were measuring in the standard cavity, and in purple is the same measurement, but done in a sample that had a cavity. And what you see, or you don't see well in that plot, the other one, is that this resistance you measure here is actually even below the one you would have at zero magnetic field. So you really, not quantized because you're between plateau, but you still see a very strong change of the resistance. And our interpretation was, if you basically are in this, between 8 and 9, 7, and let's say that case, 6 and 7 plateau, what you have is you have this tendency of the system to make kind of stripes, but those stripes in the sample that, let's say the sample without the cavity, they tend to be distributed, in completely irregular fashion. And so you don't measure a global asymmetry. Why? Because the length scale of the stripes is maybe 10 nanometers, or the width, and the length scale over which you measure is like 100 micron. So, those things have average out if you measure on that scale. Now, when you have the cavity, what happens is you have a sort of a collective effect, which of the vacuum fluctuation, which tend to align the stripes, and that's why we see this. Now, if we measure if that is true, then of course, if we measure the sample in the other direction, we should see the anisotropy in the other direction, and indeed we see that when we measure kind of the transverse resistivity, you see that the resistivity, if we measure and try to pass the curve in that direction, the resistance that we measure is now much larger in the cavity sample than it is in the reference sample, which is something you expect. Also, you can check, okay, what happens with temperature. If it stripes, so of course should appear only at low temperature, and that's why we measured also this resistance as function of temperature, and you see that in the cavity we have this anisotropy that disappears once you reach something like between 300 and 800 millikelvin. So it's something that appears only when you have very low temperatures. And the thing which is really striking is that the effect depends really on the cavity. All the other effects that I showed you, they were not so depending on the shape of the cavity. We can have different shapes of the cavity. In that case here, you see that we compare two samples that have two different shapes of cavities and also two densities. And one has this cavity, which is really like this rectangle, and the other one has more like this cavity in H. And what we see is, in each case, we see that we do see an anisotropy, but when we have a flat edge, we basically see this amazing, strong anisotropy that I was showing, and it's the only sample in which we see this conductance going below the conductance that you have in the geomagnetic field. While the same sample, but with steps that are maybe a quarter of a micron thick, coming from the lithography, showed already a lower. It still shows the anisotropy, but it's actually shows a lower anisotropy. Here, this sample, which is less, you see, it's less symmetric. When you have a flat edge, you see a relatively strong anisotropy. And now we also have a sample in which we purposely made edges spikes, if you want. And this one shows almost no anisotropy. So it's really something that depends on this boundary condition of the resonator. So there, the explanation from, let's say, at least it's not, again, those are kind of frameworks that is not a complete explanation, but it's already a work done by the group of Eugene Demler, using basically a change of the free energy as function of the angle between the field and the stripes, that at least predicts this, this free energy that it then increases as function of misalignment. So they really showed that the free energy is lower when the electric field perpendicular to the stripes as when it is aligned with the stripes. And that is kind of so far the explanation that we have. So effectively you have a system which is thermally disordered, and then when you put the cavity, you basically force to collapse the system in one preferred position. So what I really showed you as a conclusion is that the quantum Hall effect has really a lot of it's a very rich phenomenon. And so you have the one which is the most famous is the topological insulator with the quantization of the Hall plateau. We saw that when we are looking between two lambda levels, we have this charge density waves. We saw also that the Zeeman splitting and the exchange interaction are important, or that you can do also fractional quantum Hall state. And you saw that in the end, the cavity actually had an influence on every single thing of this at different levels of this relatively rich, very rich phenomenon. So that's why I really think that the quantum Hall effect is really a very nice probe of the vacuum field effect in solid state, I think we hope to show that the hovering cavity, this cavity I can bring, is really a very powerful tool because it allows us to keep the same sample and really just look at the effect of the cavity specialized. We saw that, of course, that drastic influence on the quantization of the integer. I didn't talk about it, but we looked for renormalization of the transverse resistance. We didn't find anything so far. And, we had this improvement with the evidence of the modification of the G factor, improvement of the fractions, 1/3 family, and we have also vacuum field control of strike order. With that, I would like to thank you for your attention and welcome all questions. Thank you.
Before we start with the questions, I just want to remind the PhD students they need an attendance certificate, please fill out the name of this form. And with that, let's go to the questions.
Thank you very much for this talk and lecture. I have two questions. First is this cavity-mediated electron attraction could it lead to boson formation and substitutability? And second is also if people are talking here about the short noise of electrons, definitely quantum false state is known, but if the fluctuation of quantum field could be described as short noise of photons, and if there is any interaction between these two systems.
Thank you for this excellent two questions. So, yes, let's say the first question about superconductivity, it's clear that when you talk about kind of a cavity-mediated attractive attack, interaction, you sort of really, okay, you can do a superconductor. You need to bring the Zeeman splitting effective Zeeman to zero, which we saw actually is going there. Now, whether it will really condense, we don't know, because we have certainly not seen it, but it's definitely something we would love looking at. And there is no real theory now that we predict. Now, your question about noise is also, of course, very interesting. That on the experimental side, of course, is if you want an additional capability that we do not have, because it's measuring shot noise is something that we have to learn how to do, and we don't have this capability yet, but it's definitely something that maybe could give a kind of more experimental access to this formation, to the role of polarities. Because you see, there was all this question, if I look, because I didn't talk about the polaricon basis, because I don't think the polaricon basis is extremely useful to explain what we have. But to make a long story short, if you consider a collection of electrons having all the same transition energy, and you say now, oh, what happens if I put that electron inside a cavity? Well, then you can show that you basically can create new excitations, which are the mixture of this collective excitation of electrons and cavity photons. And this gravity coupling that I was mentioning was exactly the rate of change of exchange of those two of energy in these two systems. And now we say, well, if I add an electron, because I do transport, I add or remove an electron in my system, well, I will change the strength of that coupling by tiny bits, but I will do. And that means that in a way, there must be an energy penalty associated with that. And that also means that probably the statistics of my electron transport might be changed. So it's a very subtle effect and would be a fantastic way of probing the existence, or let's say, probing a bit more directly.
Thank you.
I mean, it's a very good question. So the question is, of course, if I now increase, if I take this collective coupling and this collective coupling is proportional to the square root of the number of electrons in the system times the vacuum field potential, and then there's nothing that would prevent you from making the coupling larger than even the frequency of the cavity, which we studied some of we did study a few systems where that happened. And then you could say, well, exactly, what is the effect on the transformer? Experimentally, of course, in the end, the experimentalist difficulty is to design a system in which this works, and at the same time, you can routine transform in a single quantum well. It turns out it may have actually, we have the, if you go back to this proposal in that time to discuss of the group of Anhubio that proposed back like 3 or 4 years ago that we would renormalize the quantum Hall effect resistance. This was actually in a model where they looked at a system where effectively they realized after the fact that they had set the cavity frequency to 0. And that, of course, assuming that they had predicted this very strong normalization, which we did not see, and then the answer was, yeah, we didn't see it. Why? Because our cavity set did not have a 0 frequency. And then, of course, the thing is, if you have a 0 frequency cavity, then the ratio of omega over the cavity frequency is infinite. And the funny thing is, we just realized recently, yes, you can have a system like that. If you take a fabric cavity and you put your quantum wells in the center, you can show that the 0 frequency mode, you create a mode where there is actually a 0 frequency, and you actually have effectively an infinite relative light matter coupling. But the interesting thing is that now we fulfill the conditions of that theory. So we're very excited. Maybe something happens.
Thank you so much, Jérôme. Very nice talk. I have also two questions. First of all, polaritons. You mentioned that it's important to focus on the polaritons. From another side, maybe I didn't get the presentation, that the effect seems like not to be very resonant. So how depend on the tuning? Probably completely not independent. So in this case, you would work with the clear quantum levels without actually typical features. The second question, maybe more deep about the van der Waals forces in general. So that reminds us of van der Waals stuff, and we know general solution, which is clearly for the van der Waals forces that we already know that all the features like the fluctuations have been captured by this general formalism, where we had all the contributions of material parameters, whatever you put there, together with magnetic field influence of these parameters. So the question is, if it's true that we have this efficient, as you said, coupling between electrons provided by the cavity, that actually would lead to the breaking down of Richter's theory, which not captures these effects, or other opportunity. And if we break down Richter's theory, that means that we will measure another Casimir force. Or another opportunity that somehow this should be incorporated inside of Richter's theory, and if it's true, that what place should be entered in the another material properties of the functional state, for example, so that is the question. If we really break down not only quantum Hall effect, but as well the first one and one.
So to come back to your question. So we started looking at those historically. The first thing we studied were actually the Schmidt-Doctor association, and at the time we saw modification where we had the capital top, and at the time Christian Schutti derived a theory based on polarity basis for the transform. And initially we're quite excited, said, okay, this is great. It sort of fitted more or less what we saw. And then, as we try to sort of fit that theory to more samples, things got worse and worse. And so in the end, I still remember I was giving a talk in the Flatiron Institute, and then he told me, because I was very happy, he said, look, we have this theory, and it's predicted, and said, well, but if you choose your basis, you can make it, you can make your theory say whatever you want. And I was like, okay. And it turned out he was right. And that's why in the end, when Cristiano came with his this cavity-assisted hopping, and I was so happy because that did not it's very the polarity basis is great for doing optics, but when you're doing electron transfer, you have this one state which has this completely different energy, and then n-1, which means a lot of other states are untouched. That doesn't really help you thinking because you don't know when I do my transport, am I exciting that state, or am I exciting that state from time to time? Or so in the end, I think for describing the transport, let's say the non-polarity basis is for me kind of the one that really works. Because then you can sum over and you can understand what it works. Now to come back to your next question about Lipschitz. Of course, I have to admit that I started reading those very classical paper, only terribly recently, the majority, of course. But I do believe it's all contained there. So I don't think there's anything new in that sense. It's just that, Vanderwaals is, as written in that fantastic paper, works well for gas, but as you try to make solid state systems, then you have this selective, you have to work with dielectric constants. And the problem, in a sense, the solving Casimir effect is very difficult because those are integrals that can do it one way or the other, and you have to remove the variables correctly and so on. And so in the end, I believe what we see in that sense is not new, but it was neglected. It was not taken into account. I don't think there is, if you want new physics, in that sense, a new interaction or something. No, I mean, those are all based on electromagnetism, as we understand. But it plays a role and gives them, in the end, measurable effects. Is that what I can now?
This is how to represent the density of the system. So you have to very high density, you have to think it's, let's say, 20 Tesla. So you have the same side perspective.
That's a very good question. You see, on one hand, if you fix, at some point, you still think, okay, if I have a cavity which is 140 gigahertz, and my cyclotron energy, when I go to 20 Tesla, is many, many millicon volts. Those two things should be coupled. How efficiently, how fast. And indeed, when we looked, again, you have to look at those effects in different ways. But let's say when we actually looked at the initial data, if you want, if I look back at the right, no, that's, let me take the first data we showed. One thing is striking, if you want, right here, let's say, if you look at the quantization of the nu equals 2 plateau in that initial sample, well, it's untouched by the cavity, doesn't move. And when we took the same sample and moved to higher field, there's no change. So at some point, when your quantum hole is strong enough, then the cavity is not able to break it. So clearly, we see the strongest effect when, obviously, the quantum hole is quantized but has competition, and therefore there's a disorder. And what we do is the cavity helps the disorder. And so I think, but this problem, of course, what you have to realize is the nature of the cavity we use does not allow us to tune the frequency of the cavity arbitrarily. Because the cavity has to be around this heavy gas, and therefore, if we wanted, for example, to make a cavity with a much higher frequency, we need to make the full bar much narrower. And that means that the physics of the transport is different. And people know that if you make a very narrow whole bar, then you almost don't see any fractions. So it is a trade-off.
You consider that the techno back scattering ballpark. Did you consider to introduce some mixing of the channels?
Yeah, that's the model. Yeah, I don't have time to explain, but that's the model we applied. So what we did is to model this effect, what we did is we used the Böttiger-Landauer type of approach. And what we said is this hopping that I was discussing before, this electron hopping, what it does, it allows us to jump at some place from one edge to the other edge. And that's, I remember having a strong discussion with Daniel Nuss initially, because I didn't jump over 40 micron. It would be true if we were sort of only considering this very high magnetic field. But in the low magnetic field region, you basically have this, this speculation view of the one hole. And it means that your internal lambda level, edge state does not only stay on the side, but maybe because of disorder is brought closer to the next edge. And then what you do is with your cavity, you just help the electrons jump from one edge to the next. I mean, from one edge state to the next, the other counter-propagating. That's our picture.
And if you see this, and you make the edges go around, do you cast the effect?
Yeah, you could, exactly. We will not numbers, but let's say it's definitely something we would like to do also, is to play now with more tags and start to do all this little thing. But what we would like to do is to have a hovering cavity and bring that cavity close to edge state where we can selectively inject edge state and see how the cavity affects the scattering of universe.
But when you apply this argument to the fractional?
Well, okay. No, what you mean, why can't we? Okay, that's a very good question. So why don't we see your argument is, let's say, why don't we see the cavity-mediated hopping in the fraction quantum hole? Well, I guess we do see it. I think it's a competition of different effects. If you look, and again, this is something I didn't have time really to discuss, but if you look carefully, and you look at the high magnetic field here, if you look at that 4/5, if you look carefully, you see that the 4/5 is actually getting worse when the cavity is brought closer. So what I believe is, and the 4/5 comes from different families, the 1/5 family, whereas the other ones are the 1/3 family. And their interpretation is that we have on one hand this cavity as mediated attractive interaction that sort of would help to enhance the fractional phenomenal effect in certain fractions, but at the same time, we also have this tendency, which is small because we have a high magnetic field, to actually enhance the cavity assisted hopping. So I think, yes, you're right. It's a good point.
Question. So you mentioned already that it's not a resonant effect, but you're kind of usually discussing it in terms of a single mode. When it's not resonant, we know we show some of our modes.
Yeah.
Do you have a feeling kind of where the other modes of these resonators
Yeah.
are?
I mean, that's a good thing in a sense, and I should stress it again, it's a question of time, is if you think those asymmetric resonators, especially the square ones, it's kind of clear what they have, because they have excited resonances that all have very similar characteristics. They all have this field in the perpendicular to the layer. And when I say the resonator is 140 gig, yes, it is 140 gigahertz, but I think you need to go to 1 terahertz before you have a field, a mode that is oriented in the other direction. And that effectively means, because it needs to fit in the middle there, and that effectively means that, effectively, as you said, we need to sum over all those. It's clear that it's not a single mode, that I'm really convinced. And how many modes you effectively need to take into account that?
questions that are Jérôme.